Fresh observations are now shedding new light on 3I/Atlas, the massive interstellar visitor that's been puzzling astronomers since its discovery. What started as excitement over finding our third interstellar object has transformed into something far more intriguing and honestly controversial. Recent data analysis reveals patterns that just shouldn't exist in natural objects. Orbital characteristics so precise they seem almost intentional. Professor Avi Loeb and other researchers are asking uncomfortable questions. What if 3I/Atlas isn't just a comet? What if it's something designed to study us while appearing completely natural? Fresh observations reveal mysteries. Recent months of intensive observation have transformed 3I/Atlas from an exciting discovery into astronomy's most controversial object since Oumuamua. Dr. Robert Warwick from the University of Hawaii, who led the discovery team, admits that new data has revealed characteristics that challenge our understanding of natural interstellar objects. The object's behavior patterns have proven increasingly difficult to explain through conventional comet models. Advanced spectroscopic analysis by the European Southern Observatory shows surface composition anomalies that don't match any known class of solar system bodies. Most puzzling is the object's thermal signature, or rather the lack thereof. Despite approaching within 0.7 AU of the Sun, 3I/Atlas shows minimal heat emission and no detectable outgassing. Dr. Michelle Bannister from the University of Canterbury noted that objects this size should be streaming gas and dust as they heat up, but we're seeing virtually nothing. The observations have split the astronomical community between those who believe there must be a natural explanation, and others who are beginning to consider more exotic possibilities. NASA's Deep Space Network continues tracking the object, but each new measurement seems to deepen rather than resolve the mystery. The scientific debate. The astronomical community finds itself divided over 3I/Atlas, with heated debates emerging at conferences and in scientific journals. Dr. Alan Fitzsimmons from Queen's University Belfast leads the conventional camp, arguing that extraordinary claims require extraordinary evidence, and we haven't reached that threshold yet. His team maintains that unusual properties can be explained by exotic but natural compositions, possibly involving nitrogen ice or other materials rare in our solar system. However, a growing faction of researchers questions this dismissive approach. Dr. Daryl Seligman from the University of Chicago, who previously proposed natural explanations for Oumuamua, admits that 3I/Atlas presents characteristics that are harder to reconcile with known natural processes. The debate intensified when thermal modeling by Dr. Marco Michelli from the European Space Agency revealed that the object's temperature distribution doesn't match any known natural body. Spectroscopic measurements show absorption lines that appear artificially narrow, suggesting either unknown physics or manufactured materials. Dr. Sarah Seeger from MIT cautioned against rushing to conclusions, but acknowledged that we may need to expand our definitions of what constitutes natural phenomena in interstellar space. The scientific method demands skepticism, yet the mounting anomalies are forcing astronomers to confront uncomfortable possibilities. The artificial origin hypothesis. Professor Abraham Loeb, former chair of Harvard's astronomy department, has emerged as the most vocal proponent of an artificial origin for 3I/Atlas. Building on his controversial Oumuamua research, Loeb argues that the object displays technological signatures that suggest intelligent design rather than natural formation. His analysis focuses on the object's perfect orbital mechanics, unusual surface properties, and lack of expected comet behavior. Loeb's calculations suggest that 3I/Atlas's trajectory shows statistical precision that would be virtually impossible to achieve naturally. The object's approach vector, timing, and encounters with multiple planets create what he calls a reconnaissance pattern consistent with systematic exploration. In his recent paper submitted to Astrophysical Journal Letters, Loeb proposes that 3I/Atlas could be a probe designed to study our solar system while maintaining the appearance of a natural comet. His hypothesis suggests that advanced civilizations might use such camouflaged objects to observe other star systems without detection. Critics argue that Loeb is making extraordinary leaps from limited data, but his mathematical analysis of the object's properties continues to gain attention from researchers who find conventional explanations increasingly inadequate for the mounting anomalies. Unusual detection pattern. The circumstances surrounding 3I Atlas's discovery reveal troubling patterns that suggest possible stealth capabilities. Dr. Larry Deneau from the Atlas Asteroid Survey noted that the object should have been detected 18 months earlier, based on its size and trajectory, yet it remained invisible to all automated survey systems until July 2025. The delayed detection becomes even more suspicious when considering the object's approach vector from the constellation Lynx, a region of sky that multiple survey telescopes regularly monitor. Orbital reconstruction by Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory reveals that 3Y Atlas entered the outer solar system in January 2024, but somehow avoided detection despite passing through well-monitored space. The object's approach direction created additional observational challenges, as it remained positioned in areas of sky that were difficult to observe from Earth-based telescopes for extended periods. Dr. Catalina Donovan from the Linear program admitted that objects this bright should have triggered multiple detection systems, but somehow it remained hidden until practically on top of us. This pattern of avoiding detection until the last possible moment really raises questions about whether the concealment was accidental or intentional, adding weight to theories about possible artificial intelligence guiding the object's approach. Suspicious orbital characteristics. 3I Atlas's orbital mechanics present statistical anomalies that challenge natural origin theories through their mathematical precision. Dr. Fatih Namouni from Côte d'Azur Observatory calculated that the object's perfect alignment with the ecliptic plane has only a 0.2% probability of occurring naturally for an interstellar visitor. More striking are the object's sequential close encounters with Venus, Mars, and Jupiter, which orbital dynamicist Dr. Mattia Galeazzo from the University of Vienna determined has only a 0.005% probability of happening by chance. The precision of these encounters suggests either extraordinary coincidence or deliberate trajectory planning. 3I Atlas will pass within optimal observation range of each planet, maximizing potential data collection opportunities about their atmospheric compositions, magnetic fields, and moons. Dr. Alessandro Morbidelli from the Observatory of the Côte d'Azur noted that the trajectory looks almost designed to provide comprehensive reconnaissance of our solar system's major worlds. The object's velocity profile also shows subtle variations that correlate with planetary encounters, suggesting possible course corrections that natural objects shouldn't exhibit. Statistical analysis by Dr. Renu Malhotra from the University of Arizona concluded that the combined probability of all observed orbital characteristics occurring naturally is less than 0.001%, forcing serious consideration of artificial guidance systems. The hidden approach strategy. 3I Atlas's approach timing demonstrates what researchers are calling strategic concealment that maximizes the object's ability to study Earth while minimizing detection opportunities. Dr. Paul Wiegert from Western University discovered that the object's perihelion passage in December 2025 coincides with Earth's position in its orbit, creating an observational blind spot that has a 7% probability of occurring randomly. During this critical period, 3I Atlas will be positioned directly behind the Sun from Earth's perspective, making detailed observation extremely difficult while allowing the object unobstructed views of our planet. Celestial mechanics expert Dr. Kleomenis Tsiganis from Aristotle University noted that this timing allows the object to study Earth's electromagnetic emissions, atmospheric composition, and artificial satellite networks without interference from ground-based observations. The approach strategy becomes more sophisticated when considering that 3Y Atlas will emerge from behind the Sun in January 2026 at optimal angles for both radio telescope detection and deep space communication. Dr. Seth Shostak from the SETI Institute acknowledged that if we were designing a reconnaissance mission to study an inhabited planet, this trajectory would be nearly optimal. The implications are unsettling. 3I Atlas appears positioned to conduct comprehensive Earth observation while maintaining plausible deniability as a natural comet. Scientific opposition and evidence. Despite mounting anomalies, many astronomers maintain strong skepticism about artificial origin theories for 3I/Atlas. Dr. Alan Harris from the German Aerospace Center argues that size estimates remain uncertain, and unusual properties don't automatically imply artificial construction. His team's thermal modeling suggests the object could be significantly smaller than initial estimates, potentially explaining some observed anomalies through natural processes. Dr. Vishnu Reddy from the University of Arizona emphasizes that interstellar objects should be expected to show unusual properties, since they formed in different stellar environments with unknown conditions. Counter-evidence includes spectroscopic data showing absorption features consistent with water ice and rocky materials, though critics note these signatures could be engineered camouflage. Dr. Julie Castillo-Roges from NASA's Jet Propulsion Laboratory points out that we've only studied 3 interstellar objects, making it premature to define what constitutes normal behavior. The scientific opposition maintains that natural explanations involving exotic ices, unusual mineral compositions, or unknown formation mechanisms remain more plausible than extraterrestrial technology. Dr. Bonnie Barati from JPL advocates for continued observation rather than speculation, arguing that patience and data collection will eventually reveal natural explanations for these apparent anomalies. However, each new observation seems to strengthen rather than weaken the case for artificial origins. Ancient origins and anomalous behavior. Age analysis of 3I/Atlas reveals characteristics that seem to defy the natural aging process expected for interstellar objects. Dr. Grigory Fedoretz from Queen's University Belfast estimates the object's age at over 7 billion years based on surface composition analysis, making it older than our solar system yet showing no signs of expected cosmic weathering. Objects drifting through interstellar space for such periods should exhibit significant cosmic ray damage, micrometeorite scarring and surface oxidation, yet 3I/Atlas appears remarkably pristine. Most puzzling is the complete absence of a comet tail despite the object's approach to within 0.7 astronomical units of the Sun. Dr. Matthew Knight from the University of Maryland noted that any object containing even trace amounts of volatiles should be outgassing visibly by now, but we're seeing nothing. Structural analysis by Dr. Jean-Baptiste Vincent from the German Aerospace Center reveals density variations that are inconsistent with typical water ice spectra, suggesting either unknown materials or artificial construction. The object's rotation period of exactly 12 hours also raises suspicions, as natural bodies typically show irregular rotation rates due to impact history and gravitational perturbations. These ancient origins combined with anomalous behavior patterns continue to challenge conventional explanations. The stealth hypothesis. The concept of deliberate concealment has emerged as a serious consideration among researchers studying 3I/Atlas, potentially related to dark forest theory implications for interstellar civilizations. Dr. Liu Cixin's theoretical framework, popularized in science fiction but based on real game theory, suggests that advanced civilizations might prefer stealth over open contact to avoid potential threats. Professor Avi Loeb proposes that 3I/Atlas represents what he calls archaeological reconnaissance, a method for studying planetary systems while maintaining the cover of natural phenomena. This hypothesis explains why the object exhibits just enough anomalous behavior to suggest artificiality to careful observers while maintaining plausible deniability as a natural comet. Dr. Jacob Haq Misra from the Blue Marble Space Institute has studied the implications of such stealth strategies, noting that advanced civilizations might prefer observation over contact to minimize risks while gathering intelligence about other worlds. The stealth hypothesis suggests that 3I/Atlas could be collecting data about Earth's technological level, atmospheric composition, and artificial electromagnetic signatures while appearing to be a routine interstellar visitor. Radio telescope monitoring by Dr. Sophia Sheikh at the SETI Institute has detected no obvious artificial signals, but sophisticated probes might use communication methods undetectable by current technology or transmit data during periods when Earth-based observations are impossible. Lessons from Oumuamua. The scientific community's handling of Oumuamua in 2017 provides crucial context for evaluating 3I/Atlas and the importance of maintaining open-minded investigation. Dr. Robert Warwick, who discovered both objects, admits that we missed significant opportunities with Oumuamua by dismissing anomalies too quickly rather than pursuing thorough investigation. The 2017 visitor exhibited unexplained acceleration, unusual reflectivity, and extreme elongation that were initially attributed to natural causes without adequate investigation. Professor Abraham Loeb's controversial artificial origin hypothesis for Oumuamua was largely dismissed by the astronomical establishment, yet alternative natural explanations have proven increasingly problematic under scrutiny. Dr. Daryl Seligman's hydrogen iceberg theory requires formation conditions so exotic they approach the implausible, highlighting the difficulty of finding natural explanations for truly anomalous objects. 3I/Atlas represents a second chance to properly investigate an interstellar visitor with advanced instruments and sufficient observation time. Dr. Thomas Zurbuchen, former NASA Associate Administrator, emphasized that extraordinary phenomena deserve extraordinary investigation, not extraordinary dismissal. The lesson from Oumuamua is clear. When faced with genuinely anomalous objects, the scientific community must resist the temptation to force natural explanations and instead pursue comprehensive investigation that considers all possibilities, including those that challenge our current understanding of what's possible in the universe. 3I/Atlas continues its journey through our solar system, carrying secrets that may fundamentally challenge our understanding of what travels between the stars. Whether it's an exotic natural phenomenon or something more extraordinary, this mysterious visitor has already forced astronomers to confront uncomfortable questions about the universe around us. The patterns are too precise, the timing too convenient, and the behavior too strange to dismiss easily. Subscribe to Stellar Tech for more investigations into cosmic mysteries that blur the line between natural phenomena and something far more intriguing. What if the most profound discovery in human history was made and then deliberately buried? We're not talking about rumors or grainy photos here. We're talking about 24 gigabytes of classified NASA data on an interstellar visitor that, well, defied the laws of physics. Data leaked by a ghost-like hacker group revealing a 26-kilometer-wide object that wasn't just passing through our solar system but was actually, actively navigating it. This is the story of 3I/Atlas, what NASA allegedly found and why they never wanted you to see it. Let's delve into the data. Event Horizon's cyber attack. So how does a clandestine group get its hands on NASA's crown jewels? According to the leaked security logs, this wasn't a brute force attack, it was surgical. In the early hours of September 2, 2025, Event Horizon executed a coordinated cyber attack that bypassed multiple layers of agency firewalls. They exploited a zero-day vulnerability in an outdated Fortran-based mission planning module, a tiny crack in an otherwise formidable digital fortress. The transfer rate was a blistering 571 megabits per second, far too fast for automated security flags to catch in time. Forensic analysts later pieced together a chilling timeline. The attackers gained initial access at 3:14 a.m. Eastern, escalated their privileges to the highest level by 3:19, and began siphoning data at 3:23. In under 7 minutes, 24 gigabytes of compressed files, including internal chat logs, draft reports, and sensitive telemetry from the 3I/Atlas intercept mission, were gone. By 3:30 a.m., the connection vanished, leaving behind nothing but a silent gap in the audit trail. Cybersecurity expert Mikko Hipponen has stated that such an attack would require nation-state-level resources, suggesting Event Horizon is far more sophisticated than a typical hacktivist group. The manifesto and distribution. A data breach is one thing, but a declaration of war on secrecy is another. Within hours of the hack, a manifesto from Event Horizon appeared on encrypted forums. Their message wasn't a boast, it was a justification. They claimed the breach was a direct response to what they termed unlawful cosmic secrecy, arguing that discoveries of this magnitude belong to humanity, not to a select few government agencies. The manifesto warned that the stolen files contained information so sensitive even senior directors at NASA were allegedly unaware of its full scope. Their language was direct: the world deserves to know what its own scientists have found. To prove their point, they began a strategic distribution campaign. Blurred screenshots and heavily redacted memos were sent to journalists and channels known for covering classified science. They specifically avoided mainstream outlets, opting for platforms that would analyze the data without an institutional filter. This drip feed of information created a groundswell of speculation that legacy media couldn't ignore, forcing the conversation into the open on Event Horizon's terms. Authenticating the documents. In the world of leaks, authenticity is paramount, so are these files real? The evidence presented by Event Horizon is compellingly layered. The leaked screenshots are plastered with authentic details, Bold, block-lettered confidential stamps, thick redaction blocks, and metadata tags showing UTC timestamps that perfectly match the breach window from NASA's own security audit. We see mission patch artwork in the corners, a stylized comet labeled 3I Atlas Int. Every document carries unique identifiers, routing codes, and internal chat handles you'd expect to see inside a major agency. Technical diagrams and draft tables use Courier font headers and bear NASA's internal digital watermark. We even see screenshots of the classic blue and white NASA email interface, with subject lines like Atlas Intercept Immediate Action Required and Telemetry Review Anomaly Detected. One partially blurred memo lists technical trajectory data, while another redacted report is marked with the access level TSSCI, denoting top secret, sensitive, compartmented information, a classification that restricts access to a small, specific group of cleared individuals. The documents bear digital signature strings ending in JPL for the Jet Propulsion Laboratory, and GSFC for the Goddard Space Flight Center, indicating a multi-center collaboration. Discovery of 3I Atlas. Before the leak, there was the discovery that started it all. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS survey in Hawaii, logged a new object tearing into the solar system at 130,000 miles per hour. Astronomers flagged it immediately. This was no ordinary comet. The object, soon labeled 3Y Atlas, measured an estimated 26 kilometers across, roughly the size of Manhattan, moving faster than any object ever observed inside the orbit of Jupiter. Veteran survey scientist Dr. Lina Takahashi, a fictional name from the leaked files, was quoted in a log. The track was so steep, the software flagged it as an error. Within hours, observatories from Chile to Arizona confirmed the numbers. The object's incoming speed of over 58 kilometers per second defied the sun's gravitational grip. Its trajectory pointed back toward the constellation Lyra, far from the ecliptic plane where most solar system debris resides. To put its size in perspective, the asteroid that killed the dinosaurs was only about 10 kilometers wide. This was over twice that, and it wasn't from around here. Impossible physics and trajectory. Here's where the story takes a sharp turn from unusual to unbelievable. Like its predecessor Oumuamua, 3I Atlas was not behaving according to the laws of physics. The leaked mission logs from July 18, 2025, show a sudden, inexplicable sideways acceleration resulting in a velocity change, or delta V, of 1.5 meters per second. The object changed course in a way that defied gravitational models. For a normal comet, such a deviation could be explained by outgassing, measured by the non-gravitational acceleration parameter A2. However, just like with Oumuamua, initial observations of 3I Atlas showed no cometary tail, no dust, and no gas coma to account for the push. Its A2 parameter was effectively zero, yet it was still maneuvering. Trajectory analysts were stumped. They ran models accounting for solar radiation pressure, gravitational pulls from planets, and every known natural force. Nothing matched the telemetry. Dr. Amy Mainzer, a leading expert on asteroids, has noted that explaining such a deviation without observable outgassing requires exotic physics or an artificial origin. The numbers kept pointing to a single, unsettling conclusion. Some force other than gravity was steering this massive object through our solar system. Surface anomalies, the armor problem. What does a 26-kilometer object from another star system look like? The first leaked images from the Intercept mission were paradigm-shattering. 3I Atlas's surface resembled no comet on file. Imaging analysts flagged a pattern of smooth, almost metallic-looking plating, broken by lines that ran too straight to be natural fractures. One analyst, quoted in a redacted chat log, called it the radiator problem, referring to a gridwork of raised ridges spaced like the cooling fins on spacecraft. These ribs cast long, uniform shadows, and their regularity caused the anomaly detection software to flag the pattern as artificial. Comparisons to known comets like Halley or 67P Churyumov-Gerasimenko fell apart. Their surfaces are jagged and chaotic. 3I Atlas, in contrast, had long stretches that reflected sunlight like polished alloy. Further spectral analysis of this reflected light showed an albedo inconsistent with any known meteoritic iron, lacking the usual chondritic features. It was too smooth, too reflective, and far too structured. Thermal signatures and heat pulses. If the surface looked engineered, the thermal data was even more alarming. According to the leaked files, Infrared arrays recorded heat vents pulsing with incredible regularity. The logs show heat pooling along the strange, ribbed seams and then bursting outward in tight, directed jets. This wasn't the broad, chaotic outgassing you see in a typical comet. These were discrete, timed pulses occurring precisely every 90 seconds, raising local surface temperatures by over 200 degrees Kelvin in an instant. The mission logs classified this as a directive motion event, a term typically reserved for spacecraft thrusters, not natural phenomena. Even more damning, trajectory analysts correlated these thermal pulses directly with the object's mysterious course corrections. After each 90-second heat burst, the intercept team logged a subtle but precise shift in its path. The efficiency of this propulsion, measured as specific impulse, was calculated to be far beyond any chemical rocket, consistent with advanced ion or plasma thrusters. Gravity couldn't explain it, solar radiation is constant, and natural outgassing is random. The evidence was building 3. I-Atlas wasn't just moving strangely, it appeared to be actively propelling itself. Chemical composition mysteries. The mystery only deepens when you look at what 3 I-Atlas was made of. Martin Cordner's team at Goddard was the first to get a full spectrum after the intercept, and the results were an instant red flag. The early spectra lit up with incredibly sharp, bright lines of nickel. In cosmic bodies, nickel almost always rides shotgun with iron. Yet in every single frame of data from 3 I-Atlas, iron was almost completely absent. Its signature spectral lines were missing. This isn't just rare. In the entire catalog of known comets and asteroids, it's unheard of. The natural formation processes that create asteroids from protoplanetary disks simply don't separate these two elements with such purity. Leaked notes suggest the isotopic ratio of the nickel was also wrong, indicating it wasn't formed in a typical supernova. The purity level was estimated to be over 99.8%, a level that on Earth requires an advanced electrochemical process known as the Mond process. Radio echoes and communication patterns. Beyond its motion and materials, the most chilling evidence in the leaked files points toward active technology. According to the logs, radio astronomers reviewing raw data from the intercept mission flagged a pattern of faint, repeating echoes in the X-band frequency range. These weren't natural radio bursts or cosmic static, they were precise, clipped signals with a high signal-to-noise ratio, bouncing back from 3 I-Atlas at regular intervals. What made this truly shocking was the timing. The interval of the radio echoes mapped almost perfectly to the 90-second rhythm of the object's thermal pulses. It was as if something was pinging the object, and the heat pulses were the response. In one of the leaked chat logs, a veteran telemetry specialist reportedly wrote, "It's like someone is pinging the probe and it's answering. The pattern is too tight for random noise." This completely changed the nature of the investigation. SETI pioneer Dr. Jill Tarter has long argued that a truly intelligent signal would likely be efficient and information-dense, characteristics that align with these alleged repeating echoes. The data suggested it could be an active, responsive probe. Expert analysis and propulsion theory. You can't discuss these anomalies without bringing in a voice of scientific courage like Avi Loeb. The Harvard astrophysicist, who famously staked his reputation on Oumuamua being alien technology, wasted no time weighing in on the 3 I-Atlas files. He argued the intercepted telemetry read like a blueprint for an advanced propulsion system. Each 90-second heat pulse and corresponding course correction was perfectly consistent with a massive ion drive or a similar engine. In Loeb's words, if you wanted to navigate through a solar system while managing heat and energy, you would use timed, directional thrust. That is what the data shows. But the most jarring evidence was a fragment recovered by the interceptor's dust collector. A leaked lab memo described a fleck of material with a lattice of silicon and doped phosphorus, arranged in layers spaced at micron intervals. The structure was noted as being radiation-hardened to a degree far beyond current human capability, suggesting it was built for long-duration travel through the harsh interstellar medium. This wasn't just a circuit, it was an artifact from a civilization far beyond our own. So what do we make of all this? A 26-kilometer object from another star system, moving at impossible speeds, making its own course corrections. It has a surface that looks like armor, a composition of refined nickel, and it pulses with heat and radio echoes on a perfect 90-second clock. And finally, there's a fragment of what appears to be a microchip. The leaked files, if authentic, present a disturbing and profound reality. The questions are staggering. What is this object's purpose? Where did it come from? And perhaps most importantly, what else has NASA found that we don't know about? Don't forget to like, subscribe, and hit the bell icon for more deep dives into the secrets of science and technology. Thanks for watching Stellar Tech. Deep beneath Jupiter's swirling clouds, where crushing pressure should destroy any organized structure, the Juno spacecraft has discovered something that really defies the laws of planetary science. April 18, 2024, marked the day our understanding of gas giants was turned upside down, when Juno's instruments penetrated deeper than ever before and found a massive organized storm system thriving in conditions that should be, well, impossible. This terrifying discovery beneath Jupiter's surface has forced scientists to question everything they thought they knew about how giant planets work and what secrets they're hiding in their depths. The mysterious central storm discovery. Buried beneath Jupiter's great red spot lies something that has left planetary scientists honestly speechless. Juno's microwave radiometer, capable of penetrating hundreds of kilometers below the visible cloud layers, revealed a massive cyclonic structure extending far deeper than any storm system should theoretically survive. Scott Bolton, Juno's principal investigator at the Southwest Research Institute, described the discovery as completely unprecedented in planetary science. The hidden storm system spans approximately 3,000 kilometers in diameter and extends at least 500 kilometers below Jupiter's ammonia cloud deck, depths where the crushing pressure should have destroyed any organized weather pattern. Unlike surface storms that dissipate when they lose energy, this deep structure appears to be feeding off Jupiter's internal heat source, creating a perpetual motion system that may have existed for centuries or even millennia. The discovery really challenges fundamental assumptions about atmospheric dynamics on gas giant planets. Traditional models predicted that Jupiter's atmosphere would become increasingly uniform with depth, but Juno's data reveals complex, organized structures persisting in regions where chaos should reign supreme. This finding suggests Jupiter's interior is far more dynamic and mysterious than anyone imagined. The beginning of the mission. August 5, 2011 marked the beginning of humanity's most ambitious journey to Jupiter, when Juno launched from Cape Canaveral aboard an Atlas V rocket. The mission was conceived by Scott Bolton and his team to answer fundamental questions about Jupiter's formation, composition, and internal structure that had puzzled scientists for decades. Unlike previous Jupiter missions that conducted brief flybys, Juno was designed for an extended orbital campaign using a highly elliptical 53.5-day orbit that would repeatedly dive close to the planet's cloud tops. The spacecraft carried 9 sophisticated instruments, including a gravity science experiment that would map Jupiter's interior mass distribution with, honestly, unprecedented precision. Juno's journey required a complex 5-year trajectory, including a crucial Earth flyby in October 2013, to gain the velocity needed to reach Jupiter. The mission faced numerous technical challenges, including designing electronics capable of surviving Jupiter's intense radiation environment, radiation levels that would kill an unprotected human in minutes. NASA engineers had to shield Juno's sensitive instruments inside a titanium vault to prevent radiation damage during the planned 37 orbital passes around the gas giant. Jupiter is the world of chaos. Jupiter's atmosphere represents controlled chaos on a scale that just dwarfs anything found elsewhere in the solar system. Juno's JunoCam and infrared instruments revealed that Jupiter's iconic bands and zones are far more turbulent and violent than telescopic observations from Earth had suggested. Wind speeds reach 640 kilometers per hour at the equator, driven by the planet's rapid 9.9-hour rotation period that creates the fastest day of any planet in our solar system. The atmospheric bands aren't static features, but dynamic rivers of gas flowing in opposite directions, creating massive shear zones where adjacent streams collide and generate enormous cyclonic storms. Candace Hansen-Koharchek, who leads JunoCam operations at the Planetary Science Institute, described Jupiter's weather as organized chaos, where small disturbances can cascade into great red spot-sized storms within weeks. The planet's atmosphere extends thousands of kilometers deep, gradually transitioning from gas to liquid hydrogen under increasing pressure and temperature. Juno's microwave radiometer detected ammonia concentrations varying dramatically with depth and latitude, suggesting complex convection patterns that transport material between atmospheric layers. This chaotic mixing prevents Jupiter from achieving thermal equilibrium, maintaining the temperature and pressure gradients that drive its perpetual storm systems across the planet's entire hemisphere. Io, the volcanic moon. Io, Jupiter's innermost large moon, represents the most volcanically active world in the solar system, with over 400 active volcanoes spewing sulfur compounds hundreds of kilometers into space. Juno's extended mission has provided, honestly, just unprecedented views of Io's volcanic activity, revealing eruptions that, really dwarf anything on Earth. The moon's extreme volcanism results from tidal heating caused by Jupiter's immense gravitational pull and orbital resonances with Europa and Ganymede. As Io orbits Jupiter every 1.77 days, these gravitational forces flex and stretch the moon's interior, generating enough heat to keep its core molten despite its small size. Alessandro Mura, from Italy's National Institute for Astrophysics, used Juno's infrared spectrometer to track individual volcanic plumes, and discovered that some eruptions reach temperatures exceeding 1,800 degrees Celsius, hot enough to melt rock instantaneously. The volcanic activity continuously resurfaces Io, making it the youngest-looking world in the solar system with no impact craters visible on its sulfur-painted surface. Io's volcanism also feeds Jupiter's radiation belts, creating a plasma torus of charged particles that contributes to the planet's deadly radiation environment that threatens any spacecraft venturing too close. Research on Jupiter's magnetic field. Jupiter possesses the most powerful magnetic field in the solar system, extending millions of kilometers into space and trapping deadly radiation that would be lethal to unprotected astronauts. Juno's magnetometer, led by Jack Connerly from NASA Goddard Space Flight Center, revealed that Jupiter's magnetic field is far more complex and honestly chaotic than Earth's relatively orderly dipolar field. The magnetic field strength reaches 4.3 Gauss at Jupiter's cloud tops, 10 times stronger than Earth's field, and is generated by electrical currents flowing through the planet's metallic hydrogen core. Unlike Earth's magnetic field, which has clear north and south poles, Jupiter's field shows irregular patterns with multiple magnetic anomalies scattered across its surface. The field appears to be generated by convection in Jupiter's outer core, where liquid metallic hydrogen acts as an electrical conductor under extreme pressure and temperature conditions. Juno's measurements revealed that the magnetic field varies significantly between different regions of the planet, suggesting complex dynamics within Jupiter's deep interior. The magnetic field creates Jupiter's enormous magnetosphere, which extends beyond the orbit of Saturn and acts as a natural particle accelerator, energizing charged particles to deadly levels that pose serious radiation hazards to spacecraft and future human exploration missions. Juno mission peaks under Jupiter's surface. Juno's gravity science experiment has, really revolutionized our understanding of Jupiter's internal structure by measuring tiny variations in the spacecraft's orbital velocity as it passes over different regions of the planet. Luciano Ies, from Sapienza University of Rome, led the gravity investigation that revealed Jupiter's core is not the solid, well-defined sphere that scientists expected, but rather a fuzzy or dilute core extending halfway to the planet's surface. The core appears to be partially dissolved, mixed with surrounding metallic hydrogen, in a way that creates a gradual transition rather than a sharp boundary. This discovery suggests that Jupiter experienced a giant impact early in its formation that disrupted its original core structure. The gravity measurements also revealed that Jupiter's atmospheric bands extend 3,000 kilometers deep into the planet, much deeper than theoretical models predicted. Yohai Kaspi from the Weizmann Institute of Science used Juno's gravity data to create three-dimensional maps showing how mass is distributed within Jupiter's interior. These measurements required extraordinary precision, detecting changes in Juno's velocity as small as 0.01 millimeters per second, equivalent to measuring the speed of a growing human fingernail from millions of kilometers away. Jupiter's formation and composition. Jupiter's formation story has been, completely rewritten based on Juno's discoveries about the planet's internal structure and composition. The traditional core accretion model suggested Jupiter formed when a solid core of rock and ice grew large enough to gravitationally capture the surrounding solar nebula gas. However, Juno's detection of a dilute core suggests a more violent formation process, involving planetary collisions that disrupted the original solid core. Tristan Guillot from the Côte d'Azur Observatory actually proposed that Jupiter may have experienced multiple giant impacts during its early formation, including collisions with Earth-sized protoplanets that scattered core material throughout the interior. The planet's composition reveals it contains between 2 and 4 times more heavy elements than the Sun, indicating Jupiter formed from materials enriched in rocks and metals beyond simple gas capture. Juno's measurements show that Jupiter's atmosphere contains water vapor at concentrations of 0.25%, which is 3 times more than previously detected, suggesting the planet formed farther from the Sun, where water ice was abundant. And the discovery of ammonia and hydrogen sulfide at varying depths indicates complex chemical processes occurring within Jupiter's interior, where extreme pressure and temperature create conditions unlike anywhere else in the solar system. Jupiter as Earth's protector. Jupiter serves as our solar system's cosmic vacuum cleaner, using its immense gravitational field to capture or deflect potentially dangerous asteroids and comets that might otherwise threaten Earth. With a mass 318 times greater than Earth's, Jupiter's gravity dominates the outer solar system and has fundamentally shaped the architecture of our planetary neighborhood. Kevin Grazier, a planetary scientist who has studied Jupiter's protective role, estimates that Jupiter reduces the impact rate of long-period comets on Earth by a factor of 1,000. The planet's gravitational influence created the Kirkwood gaps in the asteroid belt, regions where asteroids just can't maintain stable orbits due to resonances with Jupiter's 11.8-year orbital period. However, Jupiter's protection isn't absolute. The same gravitational forces that deflect some objects can also redirect others toward the inner solar system. The Shoemaker-Levy 9 comet impact back in 1994 really demonstrated Jupiter's role as a cosmic target, absorbing impacts that might otherwise threaten terrestrial planets. Juno's extended observations have revealed how Jupiter's magnetosphere interacts with the solar wind, creating a protective bubble that helps shield the inner solar system from high-energy cosmic radiation that could affect planetary atmospheres and potentially harm life. The Great Red Spot Mystery. The Great Red Spot, Jupiter's most famous feature, has been continuously observed for over 350 years, making it the longest-lived storm system known in the solar system. Juno's close-up observations revealed that this massive anticyclone extends approximately 300 kilometers below Jupiter's cloud tops and reaches temperatures of -160 degrees Celsius at its summit. Amy Simon from NASA Goddard Space Flight Center has tracked the Great Red Spot's gradual shrinkage over the past century. The storm has decreased from 40,000 kilometers wide in the 1800s to approximately 16,000 kilometers today. Juno's microwave radiometer detected that the Great Red Spot is deeply rooted in Jupiter's atmosphere, functioning as a high-pressure system that rotates counterclockwise every 6 Earth days. The storm's iconic red coloration likely results from phosphorus compounds and other chemicals brought up from Jupiter's deeper atmospheric layers through powerful convection currents. Gerald Eichstadt, a citizen scientist working with JunoCam data, has created detailed maps showing how the Great Red Spot interacts with surrounding cloud bands and smaller storm systems. The storm's longevity results from Jupiter's lack of solid surface features or continents that would disrupt its circulation patterns, allowing it to persist indefinitely in the planet's fluid atmosphere. Jupiter's deep atmospheric layers. Beneath Jupiter's visible cloud decks lies a complex atmospheric structure that extends thousands of kilometers into the planet's interior, gradually transitioning from gas to liquid under increasing pressure. Juno's microwave radiometer has penetrated deeper into Jupiter's atmosphere than any previous instrument, revealing ammonia concentrations that vary dramatically with depth and latitude in patterns that really defy simple atmospheric models. Chung Lee from the University of California, Berkeley discovered that ammonia becomes depleted at certain depths, suggesting complex chemical processes and circulation patterns that transport materials between atmospheric layers. The atmospheric layers include distinct regions: the upper troposphere where visible clouds form, the deeper stratosphere where temperatures increase with altitude, and the thermosphere where solar radiation heats the thin gas to over 1,000 degrees Celsius. Lee Fletcher from the University of Leicester used Juno's infrared observations to map temperature variations that reveal convection cells extending hundreds of kilometers below the cloud tops. The deep atmosphere shows evidence of phosphine gas, carbon monoxide, and methane that really shouldn't exist at those depths according to chemical equilibrium models. These discoveries suggest that Jupiter's deep atmosphere is actively mixed by powerful convection currents that transport chemicals from the hot interior to the cold upper atmosphere, creating a dynamic system that continues to challenge our understanding of giant planet atmospheric dynamics. Juno's deep scan of Jupiter has revealed a world far more complex and mysterious than anyone imagined. From the dilute core that defies formation theories to the organized storm systems lurking beneath the clouds, Jupiter continues surprising scientists with each new discovery. The gas giant's protective role in our solar system and its extreme atmospheric dynamics make it both fascinating and honestly, kind of terrifying. These revelations prove that even after centuries of observation, Jupiter still holds secrets that could reshape our understanding of planetary science. Subscribe to Stellar Tech for more incredible discoveries from the frontiers of space exploration. What if the Big Bang wasn't the beginning but a rebirth? What if our entire 93 billion light-year observable universe is just a single object inside a much larger, older cosmos? This isn't science fiction, it's a possibility being explored by theoretical physicists, challenging our most fundamental understanding of existence. The clues might be hidden in plain sight, in the behavior of black holes and the baffling arrangement of the most distant galaxies spotted by the JWST. Let's explore this mind-bending possibility together. The standard Big Bang model. So, how did we arrive at our current picture of the universe? The story most of us know is the standard model of cosmology, first mathematically conceptualized by the Belgian priest and physicist Georges Lemaitre in 1927. It states that our universe exploded into being 13.8 billion years ago from a point of extreme density. From this intensely hot state, space itself began to expand. Over billions of years, gravity sculpted this expanding cosmos, pulling matter together to form the vast, web-like structure of galaxies we observe today. This model is incredibly successful. It explains the faint afterglow of the Big Bang, the cosmic microwave background, and it accounts for the accelerating expansion of the universe. This acceleration, confirmed in 1998, is often attributed to dark energy, which makes up about 68% of the universe. When combined with dark matter, at around 27%, it appears 95% of our cosmos is made of stuff we can't see or understand. This means that all the stars, planets, and galaxies we can observe make up a mere 5% of reality. The bottom line is the standard model, for all its successes, leaves us with the biggest questions in science completely unanswered. The black hole universe theory. What if there's a more elegant explanation? One that doesn't require inventing new particles or mysterious forces. A radical alternative, championed by physicist Nikodem Poplawski, proposes that our universe was born inside a black hole within a much larger parent universe. This idea flips our perspective on cosmic origins entirely. Instead of a singularity appearing from nothing, the theory suggests a physical process, the gravitational collapse of matter in a parent universe. Think of it like a star many times the mass of our sun collapsing to form a black hole, but on a cosmic scale. In this model, what we perceive as the Big Bang was actually the moment our universe formed inside that parent black hole. This framework elegantly resolves the issue of what came before the Big Bang, as the parent universe provides a clear preceding state. This cyclical model redefines our cosmic address, demoting our entire universe from everything that is to just one bubble in a potentially infinite cosmic foam. It also provides a physical source for the energy and matter in our universe, sourcing it directly from a pre-existing parent cosmos. In essence, the matter that makes up you, me, and the stars didn't appear from nothing, but was recycled from a previous cosmic iteration. Quantum mechanics and degeneracy pressure. Here's where things get really interesting, and it hinges on a core principle of quantum mechanics. Have you ever wondered what stops a dead star from collapsing forever? The answer lies in a rule established by the brilliant Austrian physicist Wolfgang Pauli. His exclusion principle states that identical particles, like electrons, cannot occupy the exact same quantum state at the same time. When gravity tries to crush matter into an incredibly small space, this principle creates a powerful outward push known as degeneracy pressure. The more you squeeze, the harder the particles push back. This is the force that supports white dwarfs against collapse, where matter is packed to a density of over 1 million kilograms per cubic centimeter. In even more extreme objects like neutron stars, the pressure is even greater, holding up against densities of over 100 trillion kilograms per cubic centimeter. This pressure is fundamentally different from thermal pressure, which supports a star like our Sun, as it doesn't depend on temperature at all. Proponents of the black hole universe theory argue that this same quantum pressure could operate on the scale of an entire collapsing universe, offering a mechanism to avoid the infinite singularity. The bounce mechanism. So, if a universe collapses, what happens when this quantum pressure kicks in? Instead of crushing down to an infinite point, a singularity where physics breaks down, the collapse could halt and rebound. This is the Big Bounce, a concept heavily explored in loop quantum cosmology by physicists like Martin Bojewald. In this scenario, as the matter of a parent universe collapses, it approaches the theoretical maximum density allowed by physics, known as the Planck density, which is about 5.1 times 10 to the 96th kilograms per cubic meter. At this point, quantum gravity effects become so powerful they overwhelm everything else. This force stops the collapse in its tracks and triggers a massive, explosive rebound. This rebound event would be incredibly brief but unfathomably violent, essentially resetting the cosmic clock for the new universe. To any observer inside this newly expanding region, that rebound would look and feel exactly like a Big Bang, while potentially preserving information from the prior cosmic cycle. This bounce also offers a potential solution to the black hole information loss paradox, a major conflict between general relativity and quantum mechanics. The paradox questions what happens to the information about matter that falls into a black hole if the black hole evaporates. A bounce mechanism suggests this information isn't destroyed but is instead carried through the rebound event into the new universe, preserving the fundamental laws of physics. Evidence from early galaxies. This might all sound like fascinating speculation, but where's the evidence? It might be hiding in the deepest images of our universe captured by the James Webb Space Telescope. According to the Standard Model, galaxies should build up gradually. Yet JWST is finding galaxies that are bafflingly massive and mature. For instance, the GLASS JWST Early Release Science Program, involving astronomers like Rohan Naidu, has identified galaxies like GLASS Z12 at a redshift of 12, meaning we see them as they were just 350 million years after the Big Bang. These galaxies are already 1 billion times the mass of our Sun, far larger than our models predicted was possible so early on. Furthermore, these ancient galaxies appear to host supermassive black holes that are millions of times the Sun's mass, a phenomenon that standard models struggle to explain so soon after the Big Bang. The Big Bounce model, however, offers a potential explanation, suggesting these black holes could be relics that survived from the previous cosmic era, acting as gravitational seeds. Galaxy rotation mystery. Now for another cosmic puzzle that might point to the same conclusion. In a random and uniform universe, you would expect galaxies to be spinning in all different directions, with a roughly 50-50 split between clockwise and counterclockwise rotations. But that's not what we see. A 2020 study analyzing over 200,000 spiral galaxies, led by computational astronomer Lior Shamir, found a significant imbalance. There appears to be a preferred direction of spin, and alignment across vast stretches of the cosmos. The statistical probability of this asymmetry happening by chance is less than 1 in a billion. This unexpected alignment, observed across a scale of billions of light years, implies that processes during the formation of the universe were not as random as we thought. This large-scale pattern challenges the long-held assumption that the universe is the same in all directions, a principle that underpins virtually all of our cosmological calculations. This isn't a small, localized effect. The pattern of this cosmic spin is coherent across billions of light years. Shamir's analysis shows the distribution of spin directions fits a dipolar pattern, meaning it has a distinct north and south pole just like a spinning magnet or planet. Such a large-scale coherent structure is extremely difficult to generate after the Big Bang and points instead to a fundamental property imprinted on the universe at its very creation. Schwarzschild cosmology. So, this idea of a universe inside a black hole isn't, entirely new. It actually falls under a concept known as Schwarzschild cosmology. The name comes from Carl Schwarzschild, who, way back in 1916, found the first exact solution to Einstein's field equations, describing the space-time around a spherical mass, what we now call a black hole. The model suggests that the observable universe is the interior of a black hole existing within a larger parent universe. From our perspective, the Big Bang was the formation of this black hole, and from the outside, our entire cosmos would just look like a regular black hole. The size of this black hole's event horizon is defined by the Schwarzschild radius, and for a universe with the mass of ours, this radius is, interestingly, remarkably close to the radius of our observable universe. Mathematically, the singularity at the beginning of our universe is similar to the singularity at the center of a Schwarzschild black hole. The edge of our observable universe, a sphere with a diameter of 93 billion light-years, acts much like a black hole's event horizon, a boundary from which light cannot escape to an outside observer. Black holes as universe creators. Let's take this idea to its logical conclusion. If our universe was born inside a black hole, what does that imply about the estimated 100 million stellar mass black holes in our own galaxy? It suggests that each and every one could be a gateway, a seed for a new baby universe. This paints a picture of a vast cosmic ecosystem, a multiverse where universes are constantly being born. This concept, known as cosmic natural selection and explored by physicist Lee Smolin, could even offer an explanation for the fine-tuning problem, the mystery of why the fundamental constants of physics are so perfectly set for life. If universes are constantly being created, then perhaps only those whose physical laws allow for the creation of stable black holes can themselves reproduce, leading to a multiverse dominated by life-friendly universes. This theory proposes that our universe is so adept at creating black holes precisely because it was born from one, continuing an unending cosmic lineage. Smolin's theory suggests that the physical constants, like the strength of gravity or the mass of an electron, could slightly mutate with each new universe born from a bounce. Universes with constants that are better at producing black holes will have more offspring, and over countless generations these properties will become dominant. This makes the fine-tuning of our universe for life not a lucky accident but a predictable outcome of cosmic evolution on an unimaginable scale. Torsion and space-time twisting. For a universe to bounce instead of collapsing into a singularity, you need a powerful repulsive force at extreme densities. One candidate for this force comes from an extension of general relativity known as Einstein-Cartan theory. The mathematics behind this were developed in the 1920s by the brilliant French mathematician Élie Cartan. This theory incorporates a property of space-time called torsion, which accounts for the intrinsic spin of fundamental particles. This spin is a fundamental quantum property like mass or charge that gives particles an inherent angular momentum. In standard general relativity, space-time can bend, but it cannot twist, making the inclusion of torsion a significant modification needed for this theory to work. According to physicists like Nikodem Poplawski, at the densities found inside a black hole, the interaction between torsion and the spin of particles would create a powerful repulsive force. This torsion-induced bounce would be the mechanism that creates a new universe inside every black hole, making them not just cosmic destroyers but creators. Cosmic anisotropy. The evidence for a preferred direction in galaxy spins points to a concept called cosmic anisotropy, the idea that the universe is not the same in all directions. This directly challenges the cosmological principle, a foundational assumption in modern cosmology. This isn't just about galaxy spins. Anomalies in the cosmic microwave background radiation, first noted in data from the WMAP satellite and later confirmed by the Planck satellite, also suggest a large-scale alignment. Physicist João Magueijo famously dubbed this the axis of evil because it aligned with our solar system's plane, a result so strange it had to be a mistake, except it kept showing up with a statistical probability of being random at less than 0.1%. These anomalies, once dismissed as statistical flukes or errors in measurement, are now forcing a re-evaluation of fundamental assumptions, which is exactly how science progresses. The cosmological principle of isotropy has been a cornerstone of cosmology for nearly a century, so challenging it is met with significant scientific skepticism. However, as observational data from projects like the Sloan Digital Sky Survey and the Planck satellite becomes more precise, these persistent anomalies are becoming harder to ignore. If the universe truly does have a preferred direction, it would force us to rewrite our most basic models, and would strongly imply an origin story that involves rotation, just as the black hole universe theory predicts. From the impossible galaxies seen by JWST to the mysterious alignment of galactic spins, we are faced with observations that don't quite fit our standard story of the cosmos. The idea that our universe is inside a black hole, born from a cosmic bounce, offers a potential framework to explain these anomalies without inventing new physics. It suggests we might be part of an endless cycle of creation. What do you think? Are we living inside a black hole? Let me know your thoughts in the comments below. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech.